Dear students, this video finds you healthy and safety. Please take care of yourself, be safe, don't give any shake hands, don't roam outside, as you all know. Let us dive into our course. We are discussing now nonlinear optimization, multivariable optimization. In nonlinear, we have covered single variable. Now we are going to do multivariable optimization, nonlinear with multivariable. Nonlinear, as you all know, the objective function is not linear. It has various power values, and on top of that, it has multivariable. More than one variable has to be optimized. So in that, we are going to try Lagrange multiplier method. Lagrange multiplier. This you will find in page number 67-68, and you can see there page number 67 and 68 how to do that. In page number 67 you can see that multivariable constraint optimization, and there we are doing the not all the methods, Lagrange multiplier method 2. Let us see how to solve, how to optimize using this method. Okay, so nonlinear variable. So let us say we have a optimization function. We have one optimization function which is f of x. Okay, this f of x has to be either maximize or minimize. Constraint subject to one inequality or equality constraint. Okay, so how we do that? So the optimum values of the decision variable we can do by Lagrangian multiplier method by using Kuhn-Tucker conditions. Okay, so how we do? Let us solve it with an example. Okay, so method of solution. Let the Lagrangian function, actually you have two function. One is f of x is the main function, which is the main optimization function. Another one is or objective function. Another one is condition function, g of x. Okay, so from here in Lagrange method, how we do that? By deriving Kuhn-Tucker conditions. How we do that? By this method. By how we do get the Kuhn-Tucker conditions? First you have two functions, f of x function and g of x function, right? So we have to derive two functions, two equations by Kuhn-Tucker conditions. They are by doing partial differentiation of first function, objective function, with respect to x1 is equals to lambda times, so lambda is the Lagrange multiplier, okay, and then multiplied partial differentiation of g of x function with respect to again x1. Here what we are doing, we have here two variables, x1 and x2. Let's say an example, x1 x2 variables we have. Okay, so with two variables, and you get one equation, Lagrange equation. Okay, and another equation you have derived by partial differentiating f of x, means the objective function with respect to x2, is equals to lambda times, lambda is the Lagrange multiplier, okay, and times partial differentiating g of x, the condition equation with respect to x2. So when you're doing with respect to x1, you get one equation. When you're doing with respect to x2, you get another equation. Okay, so this is the Lagrange multiplier equations. Okay, these three are the Kuhn-Tucker conditions. Okay, so lambda times g of x is, this should be 0. This should be 0. This is Kuhn-Tucker conditions. Lambda times g of x is equal to 0. When it will become 0, either this g of x 0, g of x should be, but this should follow two conditions. G of x must be less than or equal to 0, and lambda must be greater than or equal to 0. So these two equations must follow these three conditions. This side will become 0 when this becomes 0, when lambda times g of x becomes 0, but the condition is g of x must be less than or equal to 0, or lambda must be greater than or equal to 0. Okay, let us solve with an example. Okay, problem 3, page number 69. Okay, so there you can see the problem. You can see the problem. the temperature T and pressure P. The temperature T and pressure P of a process system are related by a linear equation such as 2T plus P is less than or equal to 0. Okay, and it is necessary to optimize 3.6T minus 0.4T square plus 1.6P minus 0.2P square. So determine the optimum temperature and optimum pressure of the given process using Kuhn-Tucker conditions. So what is the optimized function? We have to optimize this one. Okay, and here we assume T is x1 for ease, okay, and P is x2, temperature and pressure. What is subject to the conditional equation? So 2T plus P is less than or equal to 10, right? So bring 10 this side. So 2 in the place of T x1, in the place of P x2, right? 2x1 plus x2 minus 10 is less than or equal to 0. Here also 3.6T minus 0.4T square plus 1.6P minus 0.2P square. So in the place of Tx1, in the place of Px, so if you do that, you will get this equation. Okay. Now let us derive Kuhn-Tucker conditions. So what is the first equation you get? So lambda is a Lagrange multiplier. Okay. So the first equation you get like this. By partial differentiating f of x with respect to x1 is equals to multiplying with lambda times again doing partial differentiation g of x with respect to x1. Okay. So and then do this one. Okay. And the second equation you get with respect to x2. Then follow these conditions. First equation how you will get with respect to x1, right? So like this, see here 3.6 x1, when you only x1 partial differentiate with respect to only x1, forget about the x2. So here what you will get 3.x minus here this one, right? 2 multiply this one, right? 0.8 times x1. So forget about x, no need to do that one because we are doing partial differentiating with respect to x1 is equals to, look here, you are partial differentiating f with respect to x1, you will get this one is equals to lambda times partial differentiate g of x with respect to x1 here. So if you differentiate the partially with respect to x1, you get only 2. So lambda times 2. So when you do this, apply this one, you get this equation 3.6 minus 0.8 x1 equal to lambda. In a similar way, if you perform the second one with respect to x2, you get this equation. Okay, you get this equation. See here 1.6 minus 0.4 x2 is equals to lambda times 1 times x to the 1. So just lambda. So you got two equations. Okay, and you have to solve them to remove lambda. And you get a new equation. So keep this as it is. Okay, and this one you have to remove lambda, right? So multiply with 2, you get this equation and subtract this. Okay, so you will get, when you subtract this, these two will be removed, and when you rearrange them, you get this equation. Okay, 0.4 is equals to 0.8 x1 minus 0.8 x2. Okay, and you can just simplify this. When you simplify this, you get this, and you get this equation. Okay, if you simplify this, 0.8 x1 minus 0.8 x2 is equals to, take the 0.8 common, bring this side, so you get the x1 minus x2 equal to 0.5. So you got this equation, new equation. Okay, you got new equation, this one. So condition 3, what is condition 3? When you do these conditions, you must make lambda times g of x equal to 0, right? Which is lambda times g of x equal to 0? See here, lambda times g of x equal to 0. This should be, when it will possible, either lambda 0 or g of x must be 0, right? Choose first one, try with this one, lambda equal to 0. Which is lambda equal to 0? From the conditions, right? This one, make lambda equal to 0, and what you will get here, x1 will be 4.5, and the second equation also here, and from here also make lambda equal to 0, and you get x2 is 4. So substitute these two in the g of x. Substitute these two in the g of x. When you substitute these two in g of x, this is lambda is, you got the answer is greater than 0, right? Greater than 0. So this is not, see here, g of x must be less than or equal to 0, right? So but here you got g of x greater than or equal to 0, greater than 0. So this condition is not satisfied. This condition is not satisfied. Okay, then go to, okay, g of x equal to 0. G of x is equals to 0. Which is g of x? You got two equations, right? One is this one, okay, 2x1. We got two equations. This is one g of x, and another one is in the beginning what he has given. What he has given, this one. Okay, so just solve them. 2x1 plus x2 equal to 10 and x1 minus x2 equal to 0.5. When you solve them, you get x1 and x2. x1 and x2. Substitute them back in the g of x. Okay, and this is the optimum values. Optimum temperature is 3.5 unit and optimum pressure is 3 point. And if you want to check, substitute them back in the g of x equal g of x. Okay, substitute them back here. Okay, when you substitute here, what you will get here, 2.5, 2 times 3.5 is 7. Okay, and 7 plus 3 is 10. 10 is 0. So when you substitute them, g of x must be less than or equal to 0, right? Less than or equal to 0. So it is got 0. The condition is satisfied. The condition is satisfied. Hence these are the optimum. Hence these are the optimum units. But if you remember, when you solve the first two equations and substitute lambda equal to 0, so from these conditions, you got two equations, right? Substitute lambda equal to 0. When you solve them, okay, you got x1 and x2. When you substitute them in the g of x, that is greater than 0. So that condition is not satisfied. That's why we want to go for g of x equal to 0. Okay. So that's how, when you follow these conditions, you can understand how to solve when you have a Kuhn-Tucker conditions by Lagrange multiplier. Okay, so these are the Kuhn-Tucker conditions. Okay, and this is the Lagrange multiplier. These two are together. Okay, in the exam, if I say either Lagrange or Kuhn-Tucker, the same procedure you have to follow. Okay, I will explain one more time. When you have f of x and g of x, okay, and when you have them, just apply these conditions 1 and 2, you get two equations. Okay, solve them, you get a new g of x. Okay, and first this equal to 0, lambda times g of x equal to 0. Okay, so how you do that? Either by lambda 0 or g of x 0. How you get lambda 0? You got these two equations, right? Make lambda equal to 0 here and here. You got x1 and x2. Substitute them in the g of x, and that should be less than or equal to 0. If it is not satisfied, make g of x equal to 0 and solve them again. Okay, this is the simple way to perform. Okay, thank you. If you have any questions, let me know.